In this Matlab tutorial, we'll be extending what we learned in the last tutorial to 2D matrices, and creating a basic function to help us visualize the results. Let's suppose we have a matrix of numbers, and we're interested in a particular value. We'd like to find where in the matrix it occurs. We can use logical expressions, just like the last tutorial, and search this matrix for the number we're looking for. And then when we find it, we can plot the matrix as an image and circle the element we're looking for. This is going to be very useful later on when we're looking for Wally in a large image and circling Wally when we find him. In this tutorial, we'll learn about how Matlab indexes 2D arrays. We'll start to modularize our code so that every time we have a repeated piece of code, we write a function that we call instead of copying and pasting the code. We'll write a basic function and we'll perform basic arithmetic in Matlab. All the new functions we'll be using you can see here on the right. We're going to skip over some of the setup that is the same as the previous tutorial and jump right into the new content. We'll use for loops and logical expressions to find a number of interest in a large matrix. We'll write a function that returns a set of points which lie on the perimeter of a circle for plotting. Then we'll generate the figure you can see here. Let's move over to Matlab and get started. We're going to go ahead and skip over some of the content that we've learnt previously, like setting up plotting and generating some random data, and then plotting an image using imshow. So we're going to skip straight forwards to the new content. So if we go and run this, this is an example of the data we're going to work with in this tutorial. And because this gives us a different result every time, we're going to go ahead and use the trick that we learnt last time, which is to set the random number generator so that it'll give us the same result every time. It's going to be much easier to debug. And then later on we'll go back and remove this and make sure it still works. While we're at the beginning, I'll show you a handy trick in Matlab that I've been using in the past few tutorials, and I should probably tell you how it works. So yeah, every time I mouse over a variable, it shows me shows me the value of that variable. That's just this button here, Enable Data Tips. So if I disable that, no longer works. Enable works. So in this stand-in for an image, exactly one of these pixels is equal to 42. We want to find which one it is. So what we can do is we can use the same strategy that we used in the last tutorial, where we looped along the row until we found the number we were after. Now we just need to do that twice. We need to loop along each row or down each column, depending on which way you'd like to think about it. But what we need to do is we actually need a for loop within a for loop, one for loop to manage each dimension. The first thing we need to know is how high we need to count. So we're going to use the size function, and to use size you give it a matrix, in this case data, and it'll return the size of that matrix. So in I now should be the number of rows, and in J should be the number of columns. So this matrix is 1, 2, 3, 4, 5 high and 20 wide. So we need one for loop to manage one dimension and another for loop to manage the other. So we'll say for little I equals 1 up to big I, and then for the next for loop, J equals 1 up to big J. And then what we'll do in here is we need an if statement, just like last time. I'm going to say if data ij, now is that right? I goes from 1 up to big I, which is 5, and then J goes up to 20. Yes, this is right, data ij, not ji. If that equals the pattern, the number we're after, we should store I and j. So we should say maybe u position equals I and v position equals j. And that's wrong, because v is the vertical axis, which is I. very careful. Okay, so if we run this, U position equals 7 and V position equals 3. Alright, so if we go 3 along the 3 along the V axis and 7 along the U axis, we should find that this element here is equal to 42. We can just check that quickly. We can go data 3, 7 is 42. So that's good. And now we'll use a method that doesn't need for loops. First of all, we're going to use the find function, which returns an index. So we want to find any pixels in data that are exactly equal to 42. So if we run this, we get the number 33. And this is a little bit strange because this is a 2D matrix with 2 coordinates. So what does the number 33 mean for elements in a matrix? So Matlab has 2 types of addressing that both do the same thing. So as an example, this is element 1. It's also element 1, 1. This is element 2. It's also element 2, 1. And then 2, 3, 4, 5, 6. This is element 6. It's also element 1, 2. And so on. So what's the 33rd one? So 5, 10, 15, 20, 25, 30, 3. So this is 7 and 3. But how do we convert this using Matlab? Well, because Matlab has 2 types of indexing for the same object, Matlab has functions to convert between them. One of these indexing types is called linear indexing. The other one's called subscript indexing. So if we want to go from indexing to subscript indexing, we can use the Matlab function ind2sub. To use this function, we need to give it the size of the matrix we're dealing with. In this case, that matrix is data, so we say size data. And then we give it the index. I'll just leave that semicolon off for a moment. And we won't call this upos and vpos. We'll call it vp and up. Now it's going to return this dimension first and then that dimension. So v and then u. And let's run this. And we get index is 33, but the location is 3 in v and 7 in u. So we get the same answer as before. And what we can do now that we have 2 methods of solving the same problem, we should check that they both agree with each other. So Matlab has a function called assert, which you give it a statement that you'd like to be true, just like an if statement. And then if that statement is not true, it'll stop running your script and it'll give you an error message. So this is a great way of seeing if things work in the way you expect. So we would expect, if both of these methods agree with each other, that vpos should equal vp. So let's try that. Vpos. And then if this fails, we can type in a message that tells us what went wrong. So we can make this something sensible like methods do not agree with each other. And that didn't fail. And if let's say we make this something silly like VP equals 0, which we know isn't true, we get a failure message, an error message that tells us exactly what went wrong. So VP should equal VPOS, and also and UP should equal UPOS. Does that work? It does. So now what we want to do now that we've found the location of the pixel, we should draw a circle around it to report to the user exactly where it is. Let's write a function that we give the center coordinates of a circle and the radius, and that function should return a series of points along the perimeter of that circle that we can plot. So let's make you can click make a new function, and this will create the function prototype for you, which is pretty neat. Or if you don't want to do that, we can type it in manually. We can go function. And what does this function output? It's going to output x and y coordinates. But let's call it create circle. And what does it need? It needs the center locations. Let's call it xc and yc. And it also needs the radius of the circle. And the function has an end. What you can put in here as well is you can put some information here to help you, like so if we call, first of all we need to save this. If we save this, save it as create circle. If we call help create circle, we get a description of our function. So what does it do? So if we call help create circle, we get a proper description of our function. So that's useful when you're writing functions for yourself, and the easiest way to do this is create a variable called theta, or whatever you like, and we're going to create a bunch of angles between 0 and 2 times pi. And then we'll say x equals xc plus r times cos theta. Very important, cos takes in an angle as radians. If you want to use angles in degrees, you need to use cos d. I want to do something similar for y. We want y equals y center plus r sine theta. Let's save that. So now we can call our function xy equals create circle. We want to give it the x center, which in this case is called UC, or sorry, UP, and the y center, which is called VP, and we want to give it the radius of the circle. So we could make this a radius of 1 pixel, and then we can use the function plot, which we haven't used yet because we've so far just been plotting images. But you can use plot if you just want to plot time series data or spatial data, just lines basically. So you give it the x and y locations, and we can hit run. And because we put hold on here, it'll plot the image and then it'll plot on top of the image. So if we remove that hold on, it erases the image and then plots the circle on top. That line looks a little bit thin though. We can tell plot that we'd like a thicker line. Line width 2. Now, just to make sure everything's exactly the way we think, we can print the result to the console, so that we use fprintf like we did last time. We'll say number we're looking for is at location so the number we're looking for is called pattern. At location VU, so VP UP. Now what do we get? 42 is at location 3, 7. And when we index a matrix or an image, we're always going to read out the row number first, and then the column number. Remove setting the seed. So now we should get different data every time, and it should work every time. Next time, we're going to start to work with more realistic data.